Professor Coles. This is for marine hydrodynamics and propulsion. This is the second video for xfoil tutorial. In the first one I showed you where to download it. I actually still have the web page up here. And we went through a sequence of making polar plots. We discussed the pressure distributions and effects of transition and angle of attack. We looked at computing the angle of attack for a given lift, etc. So now we are going to, and we looked at how to dump data from a polar plot. So the lift coefficient, drag coefficient, pressure drag only, transition, locations, and moment coefficient for a function of alpha. So let me launch xfoil. On your Windows machines, you're going to be double-clicking xfoil.exe. On Mac, basically do the same. So I'm going to put a sequence of commands up on my courses page. The first one here would make a polar. So we'll do NACA 2412. Now I'm setting the foil. Now I go into op-air, where I get to set my operating conditions. I'm going to make a viscous simulation. Reynolds number, again, I'll use 5 million. Iter, I'm going to switch to 200. That's the number of iterations used in the viscous solver. Sometimes it doesn't converge. You might as well put a large number. It goes so fast. You switch it to seqp, meaning that it's going to plot the polar plot instead of the pressure distribution along the foil. And now I'm going to set the axes for that polar plot, and that's what we did not do last time. It's ppax. So I'm going to range my alpha to about low 20 degrees. So let's set this from -4 degrees to 25 degrees in increments of, say, 2. These are just plot limits. And then for CL, I'm going to range from 0 to 2 in increments of 0.5. That's fine. CD, I'm going to expand this too, because the drag does kick up at very high angles of attack when it's trying to predict the separation. I'm going to go 0 to 0.2 by 0.05. And the moment limits I will keep the same. Okay, and that's done. Now I'm going to initiate a polar plot with PACC. I will dump it to a file. Now this has to be a new file, or else it's going to try to append an old file and use that as part of the simulation. So make sure you're typing in a new file name. I'm going to put 2412 polar RE5E6, and that will be written to the directory in which this executable is running. Return. I'm not going to save a dump file. I'm just going to hit return for nothing. Now I can set the range of angles of attack. I'm going to put aseq, a sequence of alphas from -2 to 22, we'll say, in increments of 0.1 degrees. I'm going to hit return. Hopefully this will work. And there it is iterating. You can see it's starting at -2, where it was just about 0 for the 2412. It's climbing, climbing, climbing. Now we're at positive angle of attack. We're nearing a lift coefficient of 1. We're nearing a lift coefficient of 1.5. It's still in a fairly linear part of the regime, even at close to 10 degrees angle of attack, 12 degrees angle of attack. It's still in a linear. Now it's starting to taper off. So we're starting to get some separation towards the trailing edge, which is probably working its way towards the leading edge. The flow solver is also slowing down as they're having trouble. We've reached a peak CL max at, my increments are too small, but that's probably 18 degrees. And there we are coming back down. So we see where our CL max is, and we have our drag. You can see the drag is fairly constant, and then this is CD versus CL. So once the CL reaches about 1 here, the drag starts to increase, and then increases extremely rapidly once the CL reaches its max point, or actually prior to that. So CL reaches roughly 1.8, so somewhere around here. Now the drag is starting to get quite large. And these are the transition locations on the upper and lower surfaces. Okay, so let's close that. So that was the first sequence I wanted to show you. And that would have saved to a file. So I'm going to quit out of here. I'm going to hit exit. Oops, I did exit out. And again, it dumped this polar plot, which we asked it to dump. Right here, xfoil version 6.97. And again, this is what we asked for. The range of angle of attack from -2 to 22. CL, total drag coefficient, pressure drag only, moment, top transition point and bottom transition point in this file. So let's go back and restart xfoil. And I will do another sequence which is just plotting a single pressure distribution for a given angle of attack. I'll pick a different foil. Why don't we pick something like, let's maybe put some more camber in it. So let's do a 6412, that exists. And now, operations, I'll do a lower Reynolds number. Let's do 1,000,000 on this one. And again, change the iteration number to 200 from 10. We'll do a fixed angle of attack. We'll do 4 degrees angle of attack. There it is. What's the lift on this? It's fairly high because it has such extreme camber. You can clearly see the transitions happening here. The transition's happening about halfway down the foil. We don't have a sharp suction peak, but we're getting pressure coefficients around -1.5. So that's the velocity there is about 1.4, I guess, or so, about free stream. And decent amount of lift on this foil, and you can see the camber in this particular foil like this. Now let's go back, and let's say I wanted to know what the angle of attack was for this foil at which I had a lift coefficient of 1. So CL 1.0, return, and we'll resolve, adjust the angle of attack. It reduced it to 2.82 degrees, and that's the angle of attack needed to get this foil to be produce a lift of 1. That's about it.